webinar on recent advances in refining and assaying technologies. There is a post-end session, and the session 2, which is on assaying. We have 2 speakers for this session. The first topic will be challenges in 9999 gold assaying by cupellation. It will be presented by Mr. Simone Marsan, Head of Analytical Laboratory at Argor-Heraeus, Switzerland. A few words of introduction about our speaker, Mr. Simone. Mr. Simone Marsan is the Head of Analytical Laboratory of Argor-Heraeus, SA, based in Switzerland. He has been a part of Argor-Heraeus for the past 17 years. For 10 years, he has been involved in training, development, and validation of new analytical methods for the laboratory of Argor-Heraeus and the alignment of the methods for the other laboratories of the group. He is a Swiss Federal Swan assayer and is currently a member of some of the national and international working groups such as the LBMA Good Delivery Referees and the ISO TC 174WG1 for the standardization of analytical methods for determining the purity of precious metals. For those of you who may know Mr. Alessandro Ruffoni, Senior Assayer at Argor, you will also glad to know that Mr. Simone has had the privilege of working with Mr. Alessandro for over 17 years. With this introduction, please give a resounding round of applause as I invite Mr. Simone.
I work with Alessandro Ruffoni for these 17 years in shoulder by shoulder in my office, and I learned a lot by him in method development and for LMA purposes. So my presentation is about the result of an investigation regarding a possibility to perform fire assay in 49 gold. Why is it an investigation? Because from an international point of view, there are several alternatives to determine the gold content in materials that differs from applicability range and also for repeatability target. In this table that you can see, I summarized the most important normative written by the ISO Technical Committee 174 and the group ASTM. As you can see, the range is it goes from 5 to 59 gold, and starting from 395, only an instrumental analysis is required by the normative. So basically, the 49 gold is out of scope for fire assay. Why this? This is done because of the intrinsic precision of the method and also for the needs to determine the content of individual impurities that is a requirement for some ASTM specification. But in some cases, the range is defined as preferably. This is the case of the ISO 11426, for example, version of the year 2021. And the question that we ask ourselves is this: can a small range extension in fire assay analysis be considered? That means we can go up to 49 with this analysis. The answer is yes, or maybe the better answer is maybe, because the uncertainty must be evaluated very carefully. That means the leitmotif must be the evaluation of the measurement uncertainty and all of the contributes that can have an influence on it. The first step was to build up an Ishikawa diagrams that can be very helpful in this case to identify the contributes that are really important in this case or in this process. There are contributes that can be quite easily measured that are coming from, they're coming from the measurement, the machine, the material, and the environmental conditions. For the measurement, we must take in consideration the instruments, for the machines, for the machine, the capability of the machine that we use to do the production, and the calibration of the machines. The material is a good point. Do we have a specification? Do we know exactly what is the composition of the material that we are using in our process? And also the environmental conditions are under control or not. This is a good point. Some other points can be only monitored and not easily quantified, but are not less important. For example, the skills of the people performing the analysis, how we check it, are the good person or not. The management, how is your management of the laboratory? Do you have a good leadership or not? Is the communication of the management effective or not? These can only be evaluated, checked, and monitored, and not calculated, obviously. Going deep in the details with the fire assay process, we must consider that the fire assay analysis basically is a ratio between a final weight and initial weight of a sample, to which we apply a correction based on a variation to which we apply a factor, a correction based on a variation of the final weight on the factor. So we have an initial weight and the final weight of samples and proof test, and the contribute mainly is coming in this step from the performance of the scales that we are using. The parameters that can be considered in this case is the repeatability, the centricity, the bias, and the linearity of the scales. You can find all these parameters on the certificate that is released by the supplier of the scale itself. A different story is coming from the final weight. That means we have a final weight. The final weight, in addition to be influenced by the scale performance in the same manner, is influenced also by the process itself. That means we are doing some treatment and modification, the shape of the sample and of the proof test to be prepared for the process. So we must take in consideration the contributes coming from the purity of the metals used for the inquartation in this case, the cupellation process itself, the mechanical treatment to prepare the sample and the proof test for the analysis, and the parting in nitric acids. If we split the process into blocks, we must consider the first block, that is the inquartation, initial weightings. The second, that is the cupellation itself. The mechanical treatment done to prepare the sample for the parting. So the next one is the parting in nitric acid. And we have a final weighting. Every blocks, you see, have a sub-box. That means we have a lot of parameters to be considered, to be taken in consideration, that can be optimized and checked. The first block is the inquartation and the initial weighting. What are the parameters in this case to be taken in consideration? For the inquartation, we must consider the quality or the purity of the metals we are using to do that. In this case, we must analyze 4-9 gold. That means we must have a better quality of gold and silver to be used for the inquartation. So a suggestion, but I would say it's mandatory, to use a gold of the minimum purity of 5-9. It can be found on the market, not so easily, but it can be found. For silver, we have to consider a minimum purity of 4-9. For lead, copper, the same history, we must consider 4-9 as minimum purity. Regarding the scales, we need an accuracy of the scales of at least 0.005001 milligrams. That means a normal analytical scale, it doesn't fit for the purpose. We must use some microscales. Regarding the sample weight of the initial weight, we must keep it as higher as possible because we have an error that is constant of the aidings coming from the scale. So a good number could be 500 milligrams. That is the double of the standard weight that is a request for the normative 11426. Another good point is the environmental condition. You know, the microscales are very, very, very sensitive. So it's fundamental to keep the temperature and the humidity under control in the room where the scale are installed. These parameters are really, really important. This is because the scales can be, let's say, can have the possibility to do an internal recalibration automatically, but they are working in a certain range of temperature and of humidity. Outside the range, the precision is not granted. You receive, every time you get a scale, you receive let's say, the certificate that is issued by the manufacturer. There you can find some parameters that are fundamental, that are giving you the performance for a specific weight, for a specific scale. The next step is the compilation. You know, compilation process has been known for centuries and is working very well. And it takes the name from the name of the couples that historically are used to perform this step. They are working well. They work well for centuries. They are still working well. But a little improvement can be done using blocks instead of single couples. And that is what we decided to do some years ago. This is because the temperature inside the oven, the muffle specifically, should be as homogeneous as possible. But we have certainly small variation coming from the bottom to the top, from the right to the left of the muffle. We are doing some correction using the proof test, but they cannot do miracles. So we can increase the position-related repeatability using some blocks. You see, they are squared. The single couples maybe are not in the same line on the x-axis and on the y-axis. So these are giving more position-related repeatability. Next step is the mechanical treatment. This is a very important part of the process. The first step is the cleaning of the bits coming from the compilation. The second step is this one. We must flatten the samples before laminating and rolling them up. Historically, we are doing it using an anvil and hammer. It's a good way to do it. It's cheap and fast, for sure. But you must be sure that your anvil or your hammer has a good surface. That means you need a stainless steel hammer and a very, very flat surface and smooth. A human error can be done. That means you have the bits, someone pressing with the hammer. Maybe the error can be that the sample is not exactly in the center of the hammer, so maybe you can flatten only a corner of the sample, not all the sample, and the result could be a loss of material, so less repeatability. A good way, a better way to do that is the use of a press. There are some quite cheap, not really cheap hydraulic press on the market. These will give you greater safety and repeatability, for sure. The next step is the annealing process. First of all, why are we doing the annealing on the samples? Because we don't want cracks and loss of material. We are deforming the samples, pressing and laminating, so we can deform the internal structure of the sample itself, and we must do the annealing to avoid the cracks coming from each mechanical treatment. How is done this? Historically, it can be done with a Bunsen burner. It's really a cheap way to do it. It's a fast way to do it, but it's not the best one. This is because the flame has different areas. In these areas, we have a difference in temperature. Some areas are too hot, some are too cold, so we can have differences. And also, we must handle the sample one by one to bring them on the flame. An improvement that was done and can be done is the use of an annealing oven. We can set up a temperature, typically is 800 degrees, something like that, between 640 and 800 degrees, and get a good homogeneity inside. And also we can use also a sample tray. We can move all the sample at once and avoid any, let's say, human error. Next step is the laminating. Laminating is another fundamental step, because the gold bits must be prepared to a thickness that is typically between 0.12 and 0.15 millimeters, and rolled up tightly, but not too tightly. Why this? Because we must let the acid enter in the rolls and do the parting, so they cannot be so tight. First of all, we must check the thickness of every single lamine with the gauge. This is because we must be sure that all the lamine have the same thickness, or at least we must grant that in an analytical series we have all the same thickness for all the samples. Regarding the rolls type, we can choose. Worldwide, I've seen the S shape, the B shape, the spiral shape. I've seen this in Japan, this in Switzerland, this also in Switzerland, or in China maybe. This was done, and the last time I was there. It doesn't matter. All the shapes are working well. The most important thing is that all rolls must have exactly the same shape. The last step, but not the least, is the parting. How we do it? An historical way to do the parting is the use of the Keldal flask. You can find on the market this type of instrument. You have 6 position with 6 flasks. This is my old way to do things. But an improvement can be the use of a basket instead of the single flask. This is a drawing of a type of basket. On the market, there are some quartz basket, platinum basket, or also titan baskets. You can find what you want now in the market. These allow us to have a better temperature distribution. That means we must be sure that the liquid, in this case is nitric acid, is not boiling too strongly. Because if we have a very strong boiling solution, this can be the result can be a damage in the rolls inside the flask. With this solution, you can have a better control and avoid this problem. This is what I call the English method to perform this type of digestion. Quartz is definitely cheaper than platinum. A basket, I have some basket of this shape of platinum. That's the weight is 1.5 kilos of platinum to be stocked in laboratory for years. But they are very strong, but not cheap at all. Now, the question is, how can I calculate mathematically our incertitude of measurement or the incertitude of my system? In the table, you see, I put what I think are the 5 main contribute to the uncertainty. We have a contribute coming from the repeatability of the laboratory on the samples, that here is called A. We have the same contribute coming from the repeatability of the factor, this here is called B. You have the contribute coming from the weighting uncertainty, that means the scales, this is called C. And also the final 2 are the 2 contributes coming from the purity of the gold used for proof test. At least we need 5.9 for gold and 4.9 for silver. Accordingly to the law of propagation of the uncertainty, if the contributes are not correlated one each other, we can use this formula. We have the contributes A power 2 plus B power 2, C power 2, D power 2, E power 2 under square root. In this way, we can calculate the combined standard uncertainty. It is not unfortunately, it's not our final uncertainty, because starting from this value, we can calculate the expanded uncertainty. That means we can take this value and multiply it by 2 or by 3, depending on what is our confidence level. If you want a confidence level of 95%, we must multiply this value for 2. If you want a 99% of confidence level, we must multiply this value for 3. Worldwide is a kind of standard, the use of K2, for 95% of confidence level. Once I have calculated my uncertainty, am I happy or not with it? If I'm not happy, how can I reduce it? I can be working in two ways. The first is to work on statistical errors and systematic errors. Statistical errors are related to the standard deviation, the typical standard deviation of the method. How can I can improve the repeatability of the process. That means going back step by step in my process and optimize what can be optimized. The second is working on systematic errors. Systematic errors are related to an inaccuracy of the system. These can be optimized using better gold and silver for inquartation, for example, and can be checked participating to a proficiency testing scheme. This is mandatory for the laboratory that are accredited ISO 17025, and it is a good way to check the system. You receive at the end of the proficiency testing scheme a result given by a number. This is called Z-score result. If you are in line with the other laboratories that attended this proficiency testing scheme, you can be happy. If you are not in line, that means you must apply corrective actions. This is the best way to check the inaccuracy of the system. Once we have finished with this step, we can work on the number of replicates. This is because the standard uncertainty of the mean of n replicates, here is called UN, can be expressed this way. UN is the standard deviation of my method divided for the square root of the number of repetitions. So the next question is, how many repetitions for my sample? If I want to analyze a 4.9 gold, how many repetitions should I do? I put here a mathematical example of this. If we start using a method that has a standard deviation of 0.07 per 4,000, it's just an example, and we consider the same standard deviation for sample coming from sample and coming from test, we can use this formula to calculate the UC. Obviously, this must be divided by the square root of the number of repetition. So at the end, we have these numbers. If we use, starting from 0.07, 2 replicates for the sample and 1 replicate for the proof test, at the end we will get 0.09 per 4,000. If you double the number of replicates, we have 4 replicates, 2 proof tests, we get 0.06. If you double again, we have 8 replicates, 4 proof tests, and a final uncertainty of 0.04. These are very important numbers because if you consider one sample, if you want to get 0.04, you must prepare 8 samples and 4 proof tests. That means for one sample, I must do 12 analyses. It's a lot of analysis. So, what is interpretation of the uncertainty? Once I have calculated my uncertainty, I have calculated the number of repetitions that I want, what is the approach to be taken? The ISO approach is this. The measurement uncertainty must be covered by the party assuming the duty of proving conformity or non-conformity. And so it's the same party that is carrying out the measurement. That means, from a point of view of a producer, if we want to produce 4.9, we must produce, the gold content must be 4.9 plus the uncertainty. This means that for the producer, uncertainty is definitely a cost. In this case, here we have 0.04 per 4,000 at least. At the end, we must produce 4.9 at 494. So we are giving as a gift to our customers 40 milligrams of gold each kilos. It's a lot of money, to be honest. So the conclusion are these. The fire assay on 4.9 can be considered as an alternative to spectrometric method, but only after a careful assessment of measurement uncertainty. The other conclusion is that an increase in the number of standard repetition must be taken into consideration. With respect these two normatives that I taken in consideration. I learned this morning that there's an Australian standard regarding 4.9. Thank you. If you want to know more, you can go to the website of the ISO organization or to the ASTM organization. You can see also the EuroChem org is giving us the way to calculate the uncertainty. If you want to go deeper in the details, you can go here, the website of LBMA. You see the Assaying refining conference of the past years, and some years, in these 2 years, and some presentation were done by my colleague Alessandro Ruffoni. The question is, why is this one making the difference? Because normally in the oven, you have a muffle. Inside the muffle, you have a temperature control given by some sensors.
Composition of magnesium oxide cupel.
Cupel.
Cupel inside the certain impurity is not higher. Will it affect
Iron inside the couples? Never found, to be honest. I'm using some, let's say, standard couples. Nothing special. There are
specification for cupel for 4.9 analysis?
no, but you must be sure that you have a flattened surface and you don't have cracks inside, because some drops of metals can go down in the cracks, and you will get some loss of materials. But these are better not because of the quality, because they are square, and you must control better the position in the muffle. That means, you see, for perspective, if you put these 36 couples inside the muffle, you have to look inside the position, and maybe you can do some error. Just this case, for example, you have this is at a different depth of this one. And because you are doing correction using proof test, the position of the proof test is fundamental in this case. Normally, in my laboratory, when we use single couples, we are putting the proof test here, 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 and here. This is because we have a little difference in temperature from the bottom to the top, from the right to the left. In this case, if you use these blocks, it's easier to get the proof test here in the same line because of perspective.
Yeah, actually, sir, I want to say something. Actually, I think he's asking about the composition of the pupils. In India, we are also getting the local pupil from the supplier that is not exactly made from the magnesium oxide. So that quality may be impacted. For example,
Okay.
we are using Atlantic pupil that is exactly made of magnesium oxide. When we are doing the pupillation by using this individual or block, we are getting a consistency in the results. But when we are using the Indian pupil that is made of simple plate, that of the capacity.
There are two plates. The surface is two plates. Yes, it makes the difference. It's making absolutely.
Uniformity. If you use the block, then you get the uniformity in the results.
Yeah.
Here we have that is the another concern.
Okay.
Material composition.
Yeah.
Normally, it's a kind of know-how of the supplier. Another point is to check before using the capability to absorb the right quantity of lead, because a normal copper should absorb 6 grams. This is the number 1 or number 2, I don't remember. They should absorb at least 6 grams of lead. If you use good quality couples, you can absorb 6 grams. If you don't have a good couples, maybe the absorption capability is less than 6.
I have 2-3 questions. One is regarding the size of holes in the cupels.
Yeah.
Whether size of holes also affect the absorption of the lead. Second, how much should be the weight, the standard weight of lead we should take for the cupellation. Third question is regarding. I forgot third question. I'll come back later.
Okay.
Yes.
So the choice of the
yeah, one more thing. Some metals which are not absorbed by this cupels. So what should we do to arrive at the purity of gold? Like some metal, like nickel is there, or palladium is there, and some other metals are there. which are not absorbed by the through lead process. So what should we do?
Okay, so first, the choice of the couples, the dimension. The choice of the couple depends by the quantity of the lead I'm adding to the sample itself. The more deleterious elements I have inside the sample, the more lead I must add for the inquartation. So the bigger will be the couples. The couples must absorb at least the 6 grams. That means and this couple is the number 2. The weight of this couple is 12 grams. So normally the choice is linked to the quantity of lead, because the couples must absorb the 50% of his weight in lead. That means if you want to absorb 6 grams, we must use a couple of at least 12 grams of weight. If you add more lead, we need a bigger couple. Yeah, I asked you. It's okay, the answer?
How much lead we should take for this?
There's a formula. You can calculate the lead depending of the copper you are using as for the proof test. That means you are building up a proof test with the same composition of the sample you are analyzing, and the copper of the proof test is representative of the total quantity of the impurities in the sample itself. So we use a kind of simple formula to calculate the lead to be used. It is the quantity of copper divided for 12.5. This is a pragmatic way to do. You are using the same. We are the same school. So we take the copper in the proof test, we divided the copper in milligrams for 12.5, and we transform the result in grams of the lead to be used.
So there can be some alloys which don't contain copper, gold alloys.
Yeah.
So in those cases, we just add some small 5 milligram of copper to avoid spurting when the cupellation is in process. So my question was, when in that case the quantity of copper is so small, how will you calculate the
Normally we add, in this case for 49 gold, we add 20 milligrams of copper in the sample for the same reason.
Yeah.
To let the mechanical treatment working better, because this step, the copellation step should remove all the metal that are not precious from our sample, from our proof test. But we realized during the years that the 5% of the copper that you put in the sample remains in our bits. So it helps with the mechanical treatment. We do that. We add the 20 milligrams to the sample and to the proof test.
So for, let's say, have you worked on gold samples which contain nickel or palladium?
Yeah.
So in that case, what process do you follow? I mean, do we do scorification and then cupellation, or do we just do double cupellation of the sample?
Yeah, it depends by the quantity of the nickel you have inside the sample. Up to 30 parts per thousand, we are using cupellation. We
up to 30 parts per thousand.
30 parts per thousand nickel, for example.
3%, up to 3%.
2%. We use this method. We reduce the initial weight to 100 milligrams instead of 250 milligrams, and we add an extra quantity of lead. This is working well, quite well. This is our way to perform this analysis.
Can we use 250 milligrams instead of 500 grams?
So our standard weight is 250 milligrams. In this case, we are using 500 milligrams, sorry. We double the initial weight because we want to reduce the error given by the scales. We double the initial weight. We don't know if 1 gram instead of 500 milligrams is better. Never tried.
No, because the standard says 250 milligrams.
Yeah. But you can find, for example, the ISTM says 500 milligrams instead of 250. Also, the Australian normative says 500 milligrams. Yeah. Yeah.
I have a question about the scope. Actually, the scope of the ISO 11426 restricts up to 995.
Yeah.
But you are going up to 49. So this method is your accreditation of ISO 17001 or not?
So this presentation is regarding, let's say, an investigation. So my answer is yes, it could be done, but it's not our standard method. In my laboratory, we must go faster. So we must use some instrumental method that is absolutely faster than this, and cheaper also. You need an initial investment for sure that it's not so small, but you can get better results with less time. But if you don't have any instrument in your laboratory, we can start doing this analysis of 4-9 gold. Thank you very much.
Welcome, Mr. Terance Nkosi, Executive Head, SHEQ, that stands for Safety, Health, Environment and Quality, and Technical Assurance at RAND Refinery. He will speak based on his experience, lessons learned on sampling and analyzing bullion materials at RAND Refinery. Before I invite him, a brief introduction about Mr. Terance Nkosi. He is a distinguished executive head of SHEQ and Technical Assurance at RAND Refinery. With over 20 years of experience, Mr. Terance is an expert in pyrometallurgy, hydrometallurgy, and precious metals refining. He excels in overseeing metal sampling and analysis, ensuring responsible sourcing of gold and silver, and driving environmental and safety improvements. Mr. Terance has pioneered new material handling processes, enhanced health and safety records, and established a vital technical knowledge forum. As a proud South African, he values ethical leadership, talent development, and contributing to an African legacy. Currently pursuing a career as an African scholar in management and metallurgy, Mr. Terance lives by his maxim, give me the resources and I'll demonstrate the results. Over to you, sir.
Thank you for that introduction. Good afternoon, ladies and gentlemen. As I said, my name is Terance Nkosi. I'll be sharing what we've learned so far about sampling and analysis of bullion materials at RAND Refinery. Just a quick one. These are the topics that I'll be covering. For those of you who don't know where RAND Refinery is, we sit at the tip of Africa to the eastern side. We've been established in 1920 following the gold discovery in 1886. So which means gold has been mining in that region for over 140 years. We are located in Germiston, the southeast of Johannesburg, which is about 25 minutes to the airport in Gauteng, one of our 9 provinces we have, and the one that is rich in gold. Population in the region is about 6.3 million. It's slightly concentrated considering that the whole country has 60 million people. So the region is highly concentrated. In square meterage, Gauteng is smaller. And then we are fortunate that we are one of the few refineries that is still mine-owned by the mining giants, which are listed there, which is AngloGold Ashanti, Sibanye, Harmony, DRD, and Goldfields. So predominantly, many of our sources come from mined resources. In terms of heritage, we are we are an integrated single site smelter, refinery, and fabricator of precious metals. We have refined in our tenure since 1921 over 50,000 tons of gold. That is estimated to be a third of all gold ever mined. We've got a bullion coin that was introduced in 1967. We've produced over 65 million ounces of that. And then LBMA is here. So we are fortunate that you are an LBMA refiner since 1921. We've got that GDL status. Second to it is that we also a technical referee. We're one of the 5. That means that when we onboard other GDL refiners, so we do participate in that exercise. And then from the operate in 36 countries, and from what was shared from Mr. Anko Guyal earlier parts under social, we employ about 700 people to contribute to the economy under the social space. In terms of accreditation, I will not go too much to this slide, but these are the accreditations, some of the accreditations that we do have. The one I want to zoom in just for noting is the 17025 under mass metrology and the quality one. This is our process flow sheet quickly. As I said, we're 3 companies in one. One thing that we do at RAND Refinery, everything that we receive is responsibly sourced to make sure that we contribute to the sustainable market. My presentation will be centering around the bullion side, whereby we look at the types of feed that we do receive, which is the doré, the sludges, if there's any recycled gold, how it's getting evaluated. Theory of sampling, I must say, we've been participating in this world on the theory of sampling. The theory is established in 1950 by the late Dr. P.A.G. We've been in existence for over 100 years, so some of the principles we've been complying to, but with the theory, they've been strengthened. There are about 10 errors in the theory of sampling. So far, we've noted that in improving our processes and refining continuously, we make sure that those errors don't come through. For an example, in the estimation error, the global estimation error, the error margin of having a wrong sample can range between 50 to 100%, which means you can get it completely wrong. Especially for the mine gold, by the way, for this presentation, there are other deleterious elements that can come through. If you don't sample right, you can have errors that are linked to heterogeneity, which, according to the theory, you can use correct sampling errors to correct for them. For an example, in terms of segregation, if you can find it, you need to use a technology that can homogenize the melt to make sure that you can be able to extract a representative sample. In terms of method of sampling, you can look at, we've got different methods that I'll talk to you about, but the one that Mr. Simone just left us with is the weighing. If you don't have proper calibration of weights, you can get it wrong. For a deposit, for an example, of half a ton, 500 kilogram gold, 90%, if you've got an error margin of 0.1, that given yesterday's gold price, that's a $39,000 error margin per ounce. Sorry, for that error, not per ounce. We also have the analytical side, whereby the error margin is about 5 to 10%, whereby we need to make sure that the equipment that you use is calibrated, is looked at, the instruments that you use, if they drift, find ways of making sure that you get them on spec. If there's new technology, for those who are in management, the lab is very important to spend on it. You don't use things and sweat it to completion up until beyond its repairs. In terms of gold determination, there are three things that contribute to it. It's the weight, it's the sampling, and it's the assaying. So all three are very important to note. They are not linked, but they contribute to the metal content that is reliable and trusted in the market. So I'll be talking to these three. What are the lessons that you've learned? The first one, as I said, we're a mine gold refinery. What we've noticed is that after 140 years, the quality of gold has changed, and the price is encouraging people to give all sorts of gold streams, whereby we've started to notice gold that is high in copper, chrome, lead, and all these other elements. Some of them depositing customers don't have smelt houses. They do give us sludges that we can refine for them. And then we've got high purity bars. Some of the high purity bars, mainly some of the guys use drill samples that I'll talk about in one of the investigations that we did. So all these get to be dried. We've got an induction furnace. I'll mention the importance of having an induction furnace compared to a melting furnace, whereby we take samples and then roughly we take about 8 dips and 4 discs. And then this is for a small average size deposit. But if a deposit gets to be larger in size, there's a method that we do use to make sure that we increase the random sampling of the dips and the discs that we do take. We also have an ability to take pin tube and drills, and then we use fire assay, and then we use the XRF. We've got 2 XRFs that we use in comparison to make sure that we can understand the chemical makeup of the material, plus to get an estimate of what the precious metal is. But we use fire assay as our gold standard. So a quick one, what are the lessons that you've learned from weighing? I think one of the things is that in the mining process, samples are quenched in water. They are dipped before the bars come to us. So for us, it is important to dry those samples to make sure that we don't pay for moisture. So we dry it at 350 degrees, whereby because of that 17025 accreditations that I've mentioned on quality, we make sure that the ovens that we do use are the latest and they dry to consistent weight before the weight is pronounced. also, what we've noticed is that the calibration of scales, that's why we had to go for 17025 accreditation on mass metrology, which means we've got in-house skills to make sure that every scale gets to be calibrated at a certain sequential intervals, and every day there's a process of calibration to make sure that we don't make an error. Our error margins are very low, so we have to have that precision. All the scales, like for example, this one, as you can see, they are linked to PLC. That's an investment we decided to make to avoid handwritten errors. Sometimes those last significant values, if they're not correctly written, can end up to errors and gold losses in a refinery. So everything is calibrated, and then it's looked at. And then because we predominantly a gold mine refiner, some of the bars that we do receive have got slag entrainment. So it is important that after we've confirmed, after taking samples, we need to make sure that we don't account the slags as part of the gold metal. And then maybe on this last side, we've invested as well in security measurements to make sure that before the gold is released, if a customer can have a dispute, everything is under observation. We've got security surveillance system to make sure that there are no issues. Anyone can come and dispute to see if, let's say, we were to pronounce the results, their question, they can see it on video surveillance. So all of this information was presented at the 2019 LBMA Technical Conference by one of my colleagues, Sandra Ratsoma. If you go to the LBMA website, you'll see some of this. In terms of sampling, I think sampling is more important. I think from taking a representative sample to represent the population according to the theory of sampling is very important, because if you get it wrong, as I said, especially in the estimation error, you can be 100% wrong. So for us, we spend time to make sure that all our operators are trained in the theory of sampling to understand what they are doing, especially with the grades, as I said, that are changing over time, to make sure that the sample that is taken, that even it goes to the lab, is properly taken. You can imagine if you employ scholars at the lab, but you employ somebody who's not educated in sampling. So it's almost like garbage in, garbage out. So if you get the wrong sample, you analyze for the wrong thing. So we spend time on this one to make sure that the sample represents the population, and that is the one that gets to be analyzed. So we understand that the gold impact is affected by the sample. So that is why for us, we spend a lot of time in training everyone, not only from the high bullion side, even from the low grade side, to understand the theory of sampling. So why do we use an induction furnace? We believe that this is the technology that helps us with two things. It helps to melt the material faster, and second, it helps with the eddy currents, with the swelling effect, so that by the time when we take the sample, we use special tools that were in-house developed to make sure that it's an iron rod that is smoked in a certain chemical, that when you extract the sample, the dips that you are extracting, or the sample dips that you'll be taking, they don't create an impurity further to the gold that is taken, but you take it at correct incremental levels. And this technology helps us with that mixing. So these are some of the samples that we do take. The dips, as I said, we're taking 8, but at the lab, on average, we analyze about 5, which we are randomly selected on a small deposit. But if the deposit is higher, obviously the number of samples that we take are higher. And then these are these samples that we, as I said earlier, we take 2 and we analyze them in our 2 XRF machines. And then we've got quality parameters to make sure that when the results come out, we compare the 2 results as well to make sure that they are in sync. And then we've got an ability to take pin tube and also the drill samples. So this is one of the papers as well that was presented in this year's Sampling and Assaying Technical Conference in South Africa, where we co-hosted. That was presented by one of my colleagues in 2024. It's available in the website. So what have we learned about sampling? Is that the sampling method is very important for the analysis. Number 2, based on the 2019 work, what we have noted is that when the purity starts to be low, especially for the pin tube, it becomes challenging, because you can take a pinch sample, but it will not be strong when you prepare it, according to what my presenter earlier. So it creates challenges. So pinch are usually good for high purity as well, but for the grades that we've seen in the mining where the gold can become 30%, pinch don't work. Drill samples, from the picture that I showed, if the bars are pure, the drill samples will work. But if you start to have other deleterious elements, people tend to drill from the softer side. The hard side is not drilled, and it gives skewed results. So those are the lessons that we've learned. Some of the bars, when we take samples, despite trying to melt, after melting it in an induction furnace, we still find challenges because, as I said, from the earlier picture, with the impurities that we have, it's not easy to get a homogeneous sample whereby we play open cards with depositing customers to say, can we flux the material to clean it up a bit so that we can take a representative sample? Everything is done under scrutiny, and they are welcome to bring in a representation to see all the processes whereby they can see the process. I think the other thing that we picked up as well, especially for the mined bars, is that it is important to eliminate for the slags, because you don't want to pay for the slags as part of the gold. I will not talk to this slide in terms of analytical. The prior speaker did some justice to it, except to re-emphasize some of the technologies that we use for fire assay, especially around weighing. The part I concur with is that the scales, especially if you use fire assay, it is important to have proper calibration of your scales. What are the lessons that we've learned from the analytical side? Is that some of the materials that we do get have got other impurities. So we use XRF as a shed to confirm so that we can apply proper techniques to deal with that. Fire assaying is time consuming and costly, but I think for us from Refinery side, we spend time to make sure that all our analysts are trained, the skills that we have. We're fortunate that the tenure of our skills exceeds over 15 years at minimum. So it makes that investment worthwhile. In terms of safety and environmental concern, again, the skills play a very important role. And again, from the lab side, we're fortunate that there's no one who has been injured over 30 years. Bad quality bullion for us, we've noted that irrespective of taking samples, sometimes it does need the touch of a bit of fluxing. That is done, as I said, in play open cards. In terms of taking the samples to the lab, as I said, we take 5 replicates that gets to be analyzed. Most of our people in the market, we've noted that they analyze 3 or 4 times, but for us at Refinery, we take 5 replicates, and we make sure that before we pronounce the results, the quality on those is in check. The fire losses during experiencing the fire assay, we've got some validated methodologies that we do look at to make sure that, to the prior speaker that is also talked about, we've got data that we do use to confirm, and that is subject to audits and scrutiny. In terms of quality and governance, we do participate in local and international round robins to test our methods. We also produce in-house standards, reference standards. If in case the material changes, we do manufacture our own reference standard. We also produce certified reference standards that go to other people. We also use that process as a process of benchmarking and checking whether our results are in line. And then we also invest in a lot of software. We've got, when there's a new update on the LIMS, we do invest in it. In the advent of knowledge, we invest as well in Power BIs to make sure that all the information can be tabulated and extract the meaningful data and make decisions on that. So let me take you through to the quick test work that we did earlier late last year and early this year, whereby we took 60 deposits, mine deposits, because of the varying range, where we wanted to understand what is the difference between deeps, drills, and this sampling. So from those 60 deposits that we started off with, we realized, as I said, that when the quality get low for pinch up, it becomes challenging. So we ended up amending the test work to say we'll focus at the purity of 80%. That led us to have 47 deposits, which are 80% and above from 21 depositing customers. Those are mined customers, mined mine doré. Each result they were repeated 5 times on the 3 techniques, and then we made sure that we looked at the standard deviation. For the outliers, we eliminated them using the Krabs test. So this is an example of how we did it. So that if they were outliers, the ones that are marked in red, they were eliminated. Then we looked at the standard deviation and the average. So what did we find on those 47 deposits? This is the graph that we presented, is that when you looked at it, you could see from some of the plots on the bar chart graph that there were some that were low, but it was not enough to make a conclusion. Then we look at the standard deviation scatter plot, where you can see from the results that from the disc drillings, that the green bars were sort of like elevating quite a lot, followed by the pin tube, and then the D samples, 1 or 2 points were high, but seemingly it was consistent. So this one was also not enough to make a meaningful assessment. So what we did is that we used the 11 test to make sure that we understand, and then we started to compare the equal variances, is that between the dips and the pin tube, we didn't see much difference. Between dips and these drillings, there was slight difference, but this was not much. But a big variance when we used the work, we saw the difference was seen between pin tube and these drillings. So following this, we wanted to investigate further what is the cause of this, given the purity. We took the bars with the highest standard deviation. Then we noted that there were traces of iron and nickel in them. And then we used the scan electron microscope, whereby when you looked at it, it looked like that, but it was not much to see whether there was any micro heterogeneity that was brought or any segregation. So we used the magnification of 200 times EDX, and then that's what we saw, that there was nickel that was present into the product. So what can we conclude on all three? Is that the metal content is affected by weight, by the sampling, and by the analytical processes. So all three must be invested in. When you run an operation, most of the time we tend to look at the end stream and put a lot of controls there. So all these three also need stronger controls. We've noted that as the quality of the bullion deteriorates, sampling protocols need to be reviewed. Some of the things we used to believe that drills can happen, can work, but I think hopefully with this test work, you can see that sometimes it can present challenges even at higher purity, especially if you've got other elements that are not supposed to be there from historical context. At the purity of above 80, what we've noted that the pin tube and deep sampling gives similar results, and the drills showed a significant difference from the test work that I've just mentioned. Participation in benchmarking exercises improves analytical techniques. I think since we've started to join the LBMA schemes, join other schemes, we've gained a lot of insights. I think I can concur. We've also learned from a lot from Dr. Alexandro Ruffoni and other guys, Mike Hines and all those guys from LBMA. Investing in skills and competence, we cannot overemphasize it enough. As I said earlier, that in other parts of the world, we used to employ what we call school leavers to take samples, but employ scholars to analyze. Now that context for us has changed. We are looking at all across. We are going to employ scholars to take samples now. Regular audits of the laboratory and sampling process using third party, and also participating, also having third party empire laboratories in case of dispute also gives insight to improve the processes of sampling and assaying. And then following the best practice in sampling and assaying, we also invest in tools to make sure that when you extract the samples, you extract it correctly. The documentation process, it's invested in to say if there are any investigations, so that the learnings are infused into the organizations. All these are very important as an observation for the refiner and even for the depositor, so that they are protected. So in closing, I'd like to acknowledge all those people, the Refinery executive team, the melt house where we did this test work, the technical assurance that assisted us with the SEM analysis and all the work, and our chief executive, And then these are the ladies that were spearheading the test work that I've shared. And then last but not the second last, to Prof. Kim, who's leading the standard for DS73077. That is going to be converted to an ISO standard for sampling and assaying. That probably will be tabled in England in 2026. Hopefully it will have been adopted by then. And but last not the least, to the conference organizers, thank you for inviting me. Thank you.
Do you have any standard protocols for recycled gold?
We've not received a lot of recycled gold, I must say, because Refinery, most of us, as I said, we're a mine refiner. I think 99.3% of our input comes from the mine deposits. So we used to receive recycled gold years ago, but we do have standards, yes. So, but over the last 10, 15 years, we've been receiving only mine gold.
Because many of our refiners here bank on recycled gold.
Yes, I noted that. That's why I shared that the test work was predominantly from the mine gold. So hopefully I heard that the MMTC, yes, as they are venturing into the other mining and all that, maybe they can reference to this in years to come.
The quantity is so small. Getting a sample, we follow a very different process where we melt the whole thing and test it by XRF. And if it is good quantity, then we follow what he has just said, either the dip sampling or taking the sample from the melt. What we get is maximum 1 kg, 2 kgs for the recycled gold. So for that it is, for the sampling, what we do in that case, sampling means when we test with XRF, if you have a ingot, you test at 4 places at the top and 4 places at the bottom. And that's what is the sampling right now we do.
So in India, there is a regulation from banks. Basically, whenever there is a gold loan which is getting defaulted, so bank has to compulsorily auction it, the jewelry which is being mortgaged to the bank. So is there any R&D done or a research paper on how to sample the jewelry basically? I know we are talking from the refinery perspective, but that's a very important and a big market for refiners in India.
What I know is that following the ISO standard, the one that I just mentioned, it will look into that because I know that from the LBMA, there was work that was done by Dr. Jonathan Dodry on the ISO standards. So the theory of sampling, the standard that will be produced by 2026 will look into that as well to contribute. So I know that when we had the conference early in Johannesburg this year, they did mention that to some of the attendees in South Africa who were from the jewelry. They told them that there is a draft. But the S3077, which is the Danish standard, does refer to that. So I don't know what the content is at the moment of that standard.
Thank you for your time.